This is system identification, engineering efficient methods, producing data analytic solutions, and transforming data into models. What you will learn in system identification will be programming, mathematics, algorithms, statistics, and transforming data directly into mathematical models. All of these topics will be integrated into data to mathematical modeling knowledge base, enabling data analytic solutions. So what is data analytics? There are three major components: the data, the algorithms, and the programs. A system identification approach integrates these topics together for you to make data-based decisions. There are unavoidable challenges in data analytics. One of the major challenges is the high velocity of data. High data velocities produce large volumes of data that must in turn be stored. Once stored, the data is mined for information so that decisions can be made. A system identification approach to big data analytics processes the data through mathematical models. These models are usually based on the system physics and adapted in real time, thereby maximally compressing large data sets into adapted model coefficients. Therefore, low to no data storage is necessary, as only the adapted model coefficients containing the data information are stored. The system identification algorithms provided in our learning modules are robust, thereby enabling a process called information synthesis. This is where the value is created, as you are synthesizing information directly from the sampled data. Successful data analytics requires monetization. There are three primary categories: diagnostics, something has happened; prognostics, something will happen; and forecasting, what should happen in the future based on past data. System identification addresses all three of these categories. There are three primary steps to monetizing data analytics using system identification. In the data category, the data must be cleansed and resampled, followed by assessing whether the data contains useful information. In the system identification category, mathematical models are developed from the data. Next, the identified models must be validated. Once validated, the model is ready for deployment and real-time adaptation. In the impact category, insights will be gained from the model and its adaptation. From this insight comes decisions. These data-based decisions are what produces a positive financial impact. After all, your goal is to either make money or save money for your employer or your customer. So how does system identification solve data analytic problems? System identification to data analytic problems is the game changer. The process begins with measured data, computational data, or a fusion of these data sets called hybrid data. This data is analyzed using the system identification tools you will learn in this short course series to produce and calibrate mathematical models. The mathematical model is deployed and adapted in real time to precisely match the model output to the Y sensor measurement. Finally, the resulting model adaptations are processed using information synthesis to quantitatively estimate the system health by estimating the size of the problem, noted as fault size, and identifying where the problem is located, noted as the colored conic sectors. The latter is called isolation. The employment of a physics-based model minimizes false positives and eliminates the need to have a faulty data set. Let's demonstrate a system identification approach to data analytics. Shown is field data of a motor coupled to a pump. The collected data is for 13 months, just over a year. System identification relates measurements from a set of sensors to another sensor measurement. At the beginning of this data set, the motor speed is incrementally increased to the final operating speed. During this startup process, the combined motor pump model uses this data to learn this specific system from a window of data shown in red. Introducing this window as a red box, the mathematical model is obtained from this window of data. As more data is generated, the window slides over the new data set and continually adapts the model until it reaches the end of the data set. At this stage, a large volume of data has been replaced with the time history of the adapted model coefficients, thus realizing maximal data compression. These are the results after real-time model adaptation. Notice the model predictions precisely match the measurements as the model coefficients were continually adjusted. Here are the adapted coefficients in action estimating motor pump health. The initial kick in the health monitoring indicators is when the algorithm learned the motor pump system. As demonstrated by the gauges, you will see the motor begins aging sooner than the pump. As the pump wear begins to accelerate, the motor health monitoring gauge indicates that the motor health is recovering, but this is not the case. Since the pump is less efficient, it is requiring less power demands from the motor. This is why it's important to consider the system and not treat the motor and the pump as individual components. Now let's take a look at the same product line but a different individual product. Again, the kick in the indicators identify initial model adaptations. In this case, the motor initially experiences significant aging. Around 25 weeks, the pump degradation rapidly grows. As in the last case, the motor health appears to be recovering, which is not the case. There are fewer power demands on the motor by the pump. Note, the exact same model used on the previous slide was used on this slide. Therefore, you do not need to create a new model for a pump motor system as required by traditional data analytic techniques. You have a motor pump model, keep using it and adapting it. Why solve the same application multiple times? How are the adapted model coefficients used to synthesize information? Let's describe information synthesis by monitoring the health of an intake manifold on an internal combustion engine. Shown below is the mass airflow model obtained from the literature. This model uses throttle position sensor voltage and engine speed to predict the voltage produced by the mass airflow sensor. The first case is a 10% sensor bias. The top graph is a comparison between the actual sensor measurement and the model estimate before adaptation. The bottom graph shows the results of the adapted model. Comparing the healthy coefficients labeled as normal and the adapted coefficients labeled as bias, the percent change in all of the coefficients are the exact same 10%, indicating a 10% sensor bias. In the next case, the adapted coefficients shown in the table reveal small percentage changes for the coefficients associated with the throttle position sensor measurement inputs. However, the coefficients associated with RPM have a significantly larger change. Looking at the engine diagram, the path from the sensor output to the throttle plate is healthy. Therefore, whatever is happening within the engine intake is happening downstream of the intake manifold. In this particular case, there was a manifold leak. To accomplish forecasting, the velocity of the new data samples toward the green boundary is first estimated from back data samples. Using this estimate and the perpendicular distance of the black data point to the green boundary directly provides an estimate in time of how long it will take the black dot to reach the green line. This estimate is called remaining useful life. This is the structure of the courses and the provided material. There are 4 learning modules in our system identification course that ends with a capstone project. The first module introduces model parameter identification. The next module will cover data manipulation and preparation. In Module 3, statistics and discriminant analysis methods will be provided. Finally, in Module 4, a complete treatment of system identification methods for time domain modeling will be given. Each module will end with a project involving a data set. You must complete the project in each module before moving to the next. Each project requires you to write your own data analytics code. To ensure that the code you wrote is performing correctly, you will use a provided validation data set to confirm its accuracy. Upon completion of the 4 modules, you will have gained a data analytics expertise embodied in computer code that solely belongs to you. The course material provided are PDF copies of the notes presented in each module. All mathematical equations are introduced and fully described with all of its variables being fully defined. Equations will then be illustrated using visual aids so that our cohorts gain a deeper and more intuitive understanding. The lecture content and notes will also provide the associated code in each module. Line by line, the code will be explained. As each line is reviewed, the resulting calculations produced from the validation dataset will be given. It is at this time that you will be validating your code. The final module project will require you to use your new code on a new dataset to ensure that you have successfully understood the module and its contents, and thereby have the ability to diagnose, prognose, and forecast system health in real time. The impact of our system identification short course on your career is lifelong. You'll have received reference materials that combines material from a wide range of sources into one unique reference. You will have developed code applicable to data analytics and mathematical modeling from data. This code is your code, and as the programmer of this code, fully understood by you. You'll have exercised your knowledge of this short course on practice problems involving data sets specifically constructed to test your command of the technology. Finally, you'll have a unique skill set that distinguishes you from the majority of those working in data analytics. You will have the ability to solve challenging problems within a fraction of the time it takes traditional data analytics solutions, such as deep learning, with the added flair of extracting information in real time. I hope you join the data analytics movement, and I hope you join it using our system identification approach.